Berlin, Germany. Summer, 1940. According to widely repeated but officially unverified accounts, an American engineer named Paul Pleiss walks out of the Ambibud presswork factory carrying something that will save millions of gallons of fuel and countless lives. If anyone listens, he's holding a German Wehrmacht fuel container, 20 liters, 3 handles, 1 brilliant cam lever cap, and stamped into both sides an X-shaped indentation that serves 3 critical engineering functions most people will never notice. According to these accounts, Pleiss had been working in Berlin for years. He'd watched the Wehrmacht prepare for mechanized warfare. He'd seen these containers tested, dropped, frozen, baked in ovens, thrown from trucks. They don't leak. The American containers he grew up with, they leak constantly. He boards a ship to New York. He brings several jerry cans with him. He brings technical drawings. He brings manufacturing specifications. He's going to show the U.S. Army the best fuel container ever designed. The War Department will reject it. American engineers will redesign it. And that redesign will turn a perfect container into a leaking disaster that plagues Allied logistics for years. Not because they removed the X-shaped indentations, because they changed something else, something invisible, something that seemed like a harmless manufacturing shortcut, the seam construction. This is the story of how American engineers looked at German perfection, kept all the obvious features, changed one hidden detail, and created a logistics nightmare that helped lose battles in North Africa. North Africa, September 1942. American chemical engineer Richard M. Daniels steps off a plane in Egypt. He's been sent by the War Department to investigate reports of catastrophic fuel losses. What he finds is worse than anyone imagined. British quartermaster units are reporting losses of 30% to 40% between port and front line. War correspondent Alan Moorhead writes, "The great bulk of the British Army was forced to stick to the old flimsy 4-gallon container. We could put a couple of petrol cans in the back of a truck. 2 hours of bumping over desert rocks usually produced a suspicious smell." British General Auchinleck estimates 30% of all fuel never reaches its destination. In one documented case, 70,000 imperial gallons leaves the depot. 30,000 gallons arrives, a 57% loss. The quartermaster in charge reports this as a good effort. The British are using containers called flimsies, and the name tells you everything. Thin tin cans with soldered seams. 4-gallon capacity. They buckle when stacked. They split when dropped. They leak when heated. The seams fail constantly. The Americans are using their own designs, some dating back to World War I. 5-gallon rectangular cans with screw caps and cork gaskets. 55-gallon drums that require pumps. Containers designed for stationary storage, not mechanized warfare across deserts. Daniel watches fuel seep into sand. He watches soldiers struggle with containers that require wrenches, funnels, and 2 men to pour. He watches the entire Allied logistics system hemorrhage the one resource that powers everything. He sends a cable to Washington. He estimates fuel losses at 40%. In his 1987 article, "The Little Can That Could," Daniel would later admit candidly, "My colleague and I sent a cable to naval officials in Washington stating that 40% of all the gasoline sent to Egypt was being lost through spillage and evaporation. We added that a detailed report would follow. The 40% figure was actually a guess intended to provoke alarm, but it worked. Whether it's 40% or Arkinch's documented 30%, or the 57% in that specific case, the losses are devastating. Tanks running out of fuel during operations, supply columns carrying double what they need because everyone knows a significant portion won't arrive. The Germans don't have this problem. Captured Wehrmacht supply dumps are filled with green steel containers that look new even after months of desert use. Allied soldiers start hoarding them. Supply officers start requesting them by name. Within months, German jerry cans become more valuable than almost any other piece of captured equipment. British intelligence wants to know why. They want to know how German containers can survive conditions that destroy Allied ones. They want to know if this is some advanced metallurgy, some secret alloy, some revolutionary manufacturing process. It's not. It's just good engineering. Engineering that, according to those unverified accounts, an American named Paul Pleiss tried to bring to the United States 2 years earlier. Engineering the U.S. Army rejected. What is documented is this. In summer 1940, samples of the German Jerry can arrived at the U.S. Quartermaster General's office. Whether brought by Paul on a dramatic journey or through other channels, we cannot verify from official records, but the containers themselves were real, and they were remarkable. The Wehrmacht Einheitskanister was developed in 1937 by German engineer Vinzenz Grunvogel at Müller Engineering Works in Schwelm, Westphalia. The German Army officially adopted it on July 8, 1937, via Order A-HM number 324. The design is elegant 20 liters, approximately 5.3 U.S. gallons, or 4.4 imperial gallons. 2 stamped sheets of steel welded together with an X-shaped seam that runs across both faces. 3 handles, 2 short ones on the sides for one-handed carrying, 1 long one across the top for two-handed carrying or passing in a chain. The handles are recessed, so cans stack without interference. The design allows carrying 2 full cans or 4 empty ones. The cap isn't a screw top. It's a cam lever system with an internal breather pipe. Flip the lever, the seal releases, air enters through the breather, fuel pours smoothly. One person can pour the entire can in seconds. No funnel needed, no second person needed, no wrench needed. The X-shaped indentation pressed into both faces serves 3 purposes. First, it adds structural rigidity. A flat steel panel flexes under pressure. The X-shaped crease creates 4 triangular sections that are much stiffer. Second, it provides expansion relief. Gasoline expands roughly 2 to 3% when heated significantly. That extra volume needs somewhere to go. The indentation flexes outward slightly, relieving pressure. Third, when fuel cools and contracts, the indentation flexes back. No vacuum pressure develops. The result is a container designed for extreme field conditions. German testing showed minimal losses and superior durability. The can survives drops, impacts, extreme heat, and extreme cold. It's stackable, portable, and fast to use. The War Department initially rejects it. The official reason is never documented clearly. Some accounts suggest not invented here syndrome. Some suggest concerns about manufacturing complexity. Some suggest simple institutional inertia. The U.S. military has existing fuel containers, existing supply chains, existing procurement contracts. Why change? Eventually, someone at Camp Holler in Maryland takes interest. The Quartermaster Corps Research Facility agrees to evaluate the design. They measure every dimension. They photograph every feature. They test the cam lever mechanism. They analyze the steel composition. And then they redesign it American style. If you want to see how a perfect design gets ruined by manufacturing shortcuts, hit that like button right now and subscribe, because what happens next is a lesson in how invisible details matter more than obvious features. American engineers at Camp Holabird in late 1940 and early 1941 create their version of the jerry can. They keep the dimensions. They keep the 3 handles. They keep the capacity. They keep the cam lever cap. They even keep the X-shaped indentations, though they simplify the pattern slightly. What they change is invisible from the outside. The seam construction. The German jerry can use as a welded seam. 2 stamped steel halves are pressed together and electric resistance welded along the X-shaped joint. The weld is recessed below the surface. It's strong. It's sealed. It's tested extensively before the design is approved. The American version uses rolled seams. The edges of the 2 halves are folded together and crimped. It's faster to manufacture. It requires less specialized equipment. It's cheaper, and for containers holding water or non-volatile liquids, it works fine. For gasoline in desert heat, it's a disaster. Richard M. Daniel would later write, "With the authority of a chemical engineer who witnessed the consequences, as any petroleum engineer knows, it is unsafe to store gasoline in a container with rolled seams. The crimped metal joint flexing under temperature changes and impact stress develops microscopic gaps, not gushing leaks, seepage, a slow, steady loss that multiplies across thousands of containers." American engineers also remove or simplify the interior breather tube in some versions, requiring separate tools for pouring. They eliminate the interior plastic lining that German fuel cans include. These are smaller problems. The rolled seam is the critical failure. Production begins. Tens of thousands of American jerry cans shipped to North Africa, to the Pacific, to training bases, and immediately, universally, they perform worse than the German originals. The leaks aren't dramatic enough to trigger immediate alarm. A wet ring around the cap, a slight smell of gasoline, a dark stain under a stack of cans in the sun. But multiply that seepage by thousands of cans, and the losses are significant. Not as bad as British flimsies, but far worse than German jerry cans. The American jerry cans arrive in North Africa in late 1941, and throughout 1942, just as Daniel is documenting the fuel crisis. They're better than flimsies. They're worse than German originals. Allied logistics officers start sorting